Does this work as advertised? It's okay. All right. Let's get started. Please help yourself to snacks and come on in and have a seat. It's a great joy to me for me to introduce you Glenn Fredrickson, who will be up here in a moment. Long ago, I worked for Glenn at UCSB. It's been 20 years, which is staggering, probably only for the two of us. As by means of an introduction, Glenn is a consummate scientist with incredible vision, with great insight. He also seemingly has a Midas touch in the sorts and is a magician, which is among the greatest compliments you can give a theorist, that they're a magician. They can see through very complicated things and distill them down to what's important. And was a tremendous mentor for me along the ways. As a perspective on this, I first worked on a project with Glenn on a very simple reactive polymer blend. Just a couple things they could mix together and react and stuff. And it exhibited two rather nutty behaviors. And I think maybe Glenn knew this ahead of time. But the first of these was that it emulsed, it created a microemulsion. And if you don't know what that word is, it's not that important, but it made mayonnaise, is what to say. And we're all kind of familiar with that kind of icky texture of mayonnaise. And then the second thing, and just for scorekeeping, was that it was reentrant, which is particularly nutty in that this was a rare set of circumstances in this material where you could take a disordered thing and actually heat it up, and it might just assemble itself into mesophases, something that could be useful. It's a staggering kind of surprised, fun project to see. This is affectionately known in the business as the fish. So it's the microemulsion and the fish are two kind of benchmarks in my mind from these early projects. All right. Well, as I said before, I alluded to, Glenn is a remarkable scientist. You can see this in the many accolades on his profile page that was disseminated. You may have even read some of his 400 plus publications along the way. He's been lauded any number of ways, the Polymer Prize some 20 years ago, and many other things. He's also worked very strongly in the interface between the needs of industry and that of the academy. And that is something that is, I think, a remarkable achievement and a remarkable position to put ones in for making it known that humanity has a lot of interest in the problems that dovetail between industry and here at the university. All right, I should move on here. As a last note, we used to say prior to the smartphone era that if you were referring to an expert, you'd say, he wrote the book or she wrote the book on such and such a topic. And it is the case that Glenn wrote the book. As far as polymer theory goes, some 20 years ago, the book was written by Glenn, which was is also a tremendous tome on virtually everything in polymer science. That said, please join me in giving a warm welcome for Glenn Fredrickson here.
Thank you, Richard, for the kind introduction. It's hard to believe 20 years have passed. It seems like every year the time goes faster than the previous one. So I'm a soft material scientist, work with polymers and soft, squishy kinds of things. And the story I'm going to tell you today is a project that has involved a few different companies, big chemical companies, BASF, Mitsubishi Chemical, and we have a related project currently with Dow Chemical. And this is in the area of polymer formulation design. I'll tell you about those in a moment. But first, let me say a few words about the people involved. This cluster of four, these were BASF scientists. Nick was the first student on this project. Me, he, and Charles were second and third students who've kind of worked on related projects. And Chris and Kevin were postdocs who supported this program. Whoops. Seems to be frozen. May need somebody's help to get unfrozen. Yep, that works. Good, thanks. I realize I'm not going to be able to keep both sides happy with two screens, so I will, seems there's maybe a few more over here, so I'll point to this side. So polymer formulations, these are things usually mixed in either aqueous solution or an oil base. These are very familiar products. If you pick up a bottle of hairspray, you look at the label, there are probably a couple of dozen ingredients, some of which are familiar, some aren't. Includes polymers, includes surfactants, includes colorants, things that might confer different kinds of properties to the overall formulation. A lot of chemical options for mixing and matching different ingredients. And at the end of the day, you're looking for collective properties, might be interesting rheology, might result from some large-scale self-assembly within the material. And the challenge really is relating the chemistry to the properties. And if you're in a company like a Procter & Gamble trying to design these products, you know what you want in terms of the property set, and you got to figure out how do I go backwards to the ingredients. So that's the real challenge. Today, I'm just going to talk about the forward problem. If we know the chemistry, can we predict the self-assembly in the properties? Experimental challenges in this area, almost infinite design space. And in addition to being kind of unlimited in terms of the number of ingredients you can mix, even within a given set of ingredients, if you take a polymer, you can change its molecular weight. You can change its molecular weight distribution. You can consider copolymers. You can, right, the variations are amazing. Mixing things is easy to automate and high throughput. But screening properties generally isn't. So that turns out to be a bottleneck. Phase diagrams in these systems very laborious to map, refinement's slow and expensive. You might think you could go after this with some kind of molecular modeling, but again, similar problems, lots of components. You have to retain the chemical specificity to really get the behavior right. The polymers may have high molecular weights. The large structures might form in the solution from tens of nanometers to microns and beyond. Sometimes very long assembly times, could be seconds to hours for the fluid to equilibrate. So all that makes modeling approaches challenging. So the types of models that my groups worked on in the past are not atomistically faithful, but are more coarse-grained models. Matter of fact, the work that Richard did when he was at Santa Barbara was along these lines. And this is kind of the example of, you can take a very coarse-grained model of, in this case, a simple di-block copolymer with an A chemical block and a B block, describe it by a kind of bead spring type approach with coarse-grained bead elements. And there's one parameter in this model, this parameter called the Flory-Kai parameter, that describes the net repulsion between a red bead and a blue bead. And with that parameter fixed, you can predict a phase diagram that reflects the whole multitude of phases that you can find experimentally in these systems. And the phase diagram is about right. It's this chi parameter times the total degree of polymerization of the polymer that's on this axis. And this parameter F is basically the volume fraction of the molecule that's blue as opposed to red. And all these regions are regions of stability of these ordered phases. So these are very simple models, and they can predict rich phase behavior. But the problem is if you try to extend this to this formulation space, I don't know all these chi parameters. And if I have 10 components, I have a zillion parameters that would describe all the binary interactions in the mixture. And so we clearly need richer models, but the fundamental question is, how might we parameterize these coarse-grained models that can predict things like self-assembly and phase behavior without any experimental input? Because that's kind of what you'd like to do exploration. So this is the strategy that we came up with. We refer to it as a computational workflow. You need to preserve the chemistry, so we actually start at the atomistic molecular simulation scale. We will not take entire polymers, but break the polymers down into representative fragments that you can afford to simulate in, for example, explicit water or explicit oil. And then what we do is we best fit a coarse-grained model that looks like one of these bead spring models using a technique called relative entropy minimization, and I'll tell you about that in a minute. Once we've got one of these coarse-grained models, we then analytically convert the model into what's called a field theory representation. And in that representation, we can efficiently assess self-assembly and phase behavior. Okay, so that's the idea, and there are these kind of two main steps in the workflow. So first of all, what do these molecular models look like? Many of you have either know what an atomistic molecular dynamics simulation is, or might know somebody who does these on a routine basis. But basically, these are based on what are called classical atomistic force fields. So if you have a polymer molecule or some other kind of molecular species, you put force centers at the center of all the atoms in the molecule, and you have a variety of different kinds of interactions. For example, bonded interactions, angle bending potentials, torsional angular potentials, and then non-bonded through space interactions that might be electrostatic or they might be dispersive, like Lennard-Jones type interactions. And there are big packages of these things that have been parameterized based on both experiment and quantum chemistry calculations to establish those force fields. They're not perfect, but nonetheless, they're there and they're getting better all the time. The kind of coarse-grained models we want are more like these bead spring models. And what we need to do is lump a bunch of these atomic coordinates together, and usually at the center of mass, we put a bead, a bigger bead-type object. That's denoted by one of these spheres. And you can think of this process as a mapping operation where we go from small r, the set of the atomic coordinates, to big R, the set of the coarse-grained coordinates. And so the mapping operator does the center of mass kind of calculation. But we keep simpler interactions over here. We have bonded interactions between the successive beads on an oligomer or a polymer. But then we'll have various kinds of non-bonded interactions, which could be electrostatic or they could be steric in nature. All right, and generically, this coarse-grained model is going to have some parameters in it that will describe those interactions, and we'll call that set of parameters lambda. All right, so here's a little bit more detail on what those coarse-grained force fields look like, the general form that we use. So for the bonded interactions, we just use simple harmonic bonds. They might be zero-centered or displaced. And then through space, we can have some excluded volume type interactions. There, what we do is we just use repulsive Gaussians with some strength and some range. And if the net charge, if there's a net charge on these individual coarse-grained entities, we'll add Coulomb interactions. We actually regularize them a little bit, but the Barham length in the Coulomb interaction you adjust to effectively set the dielectric constant of the medium that the polymers sit in. So, you know, for this kind of a model, you've got these adjustable parameters in the model of that set. And those are the parameters that we want to try to best fit. Okay, one thing that's not really appreciated about these kind of coarse-grained models is you can give them different kinds of representations. You can obviously represent them in terms of these coarse-grained degrees of freedom, the big R coordinates. But it turns out you can exactly convert them into a field theory representation, and that's what we want to do for computational advantage. Okay, so I'm going to talk about a couple of both steps in this in a little bit more detail, and then I'll spend the rest of the presentation on some examples of executing this workflow. So the first step is if we do some all-atom simulations to get some reference statistical data about the system, how do we best fit one of these coarse-grained models? And for this, we're going to use this technique called relative entropy minimization. This is a technique developed in my colleague's group at UCSB, Scott Schell. And he's written a nice review article about this you might be interested in. But the basic idea is we're interested in minimizing this relative entropy thing, which is proportional to the log of the ratio of two probability distributions. When you take your all-atom configurations and you map those configurations, you get some data about the statistics of those coarse-grained variables. So you essentially know you have samples from the all-atom distribution of the coarse-grained variables. And then we have a model with adjustable parameters, the coarse-grained model, and we try to adjust those parameters so that the distribution of the coarse-grained model best overlaps the mapped information from the all-atom simulation. If it was perfect mapping, this ratio would be 1 and the relative entropy would be 0. That's its lower bound, and that's ideally what you'd like to get to. And you adjust the parameters in this high-dimensional parameter space until you get a minimum. So that's the idea. There are various ways you can do these things. If you have fragments of all the molecules in the mixture, usually it's a homogeneous mixture, and you can just simulate this mixture atomistically to get your reference molecular dynamics data. But we found that actually getting models that have better transferability across different compositions, it's actually nice to do this, run the simulations in the presence of a sinusoidal bias potential, which forces composition variations in your simulation cell. And so then you're fitting interactions across a broader range of compositions. So that's a trick that we tend to use in this approach. All right, the second step has to do with once I've got one of these parameterized models, how do I turn it into a field theory? And then how do I do the field theoretic simulations? So Richard talked about a book I wrote. This is kind of the book that tells you how to do this stuff, at least in the soft condensed matter world. This kind of trick has been known for 40 or 50 years in quantum many-body systems and hard condensed matter physics. And the trick we're going to use is something called a Hubbard-Stratanovich transform. And the basic idea is we're going to rewrite a partition function. That's the kind of statistical mechanical object that connects molecular configurations to thermodynamic structure and properties. We're going to rewrite that instead of being a high-dimensional integral over all those coarse-grained bead coordinates of some Boltzmann weight. We're going to rewrite it as an integral over some auxiliary field W that lives in the box. And the idea for this field W is that by introducing it, you decouple all the non-bonded interactions between the molecules. So the molecules only feel this field W. They don't feel each other anymore, all right? That's the idea. And so you reduce a many polymer problem into a one polymer in a field problem. That becomes computationally very efficient. Okay, so that's the basic idea behind this. There's a little wrinkle in this game, and the math trick that makes this work, which is essentially this little Gaussian integral identity, says that if you start out with a repulsive interaction, it takes a purely imaginary field to decouple it. So that's just a math detail, all right? But it makes then the simulation trickier because you actually have to sample these fields in the whole complex plane and not just along the real axis, all right? And this is something that those of you know about time-dependent quantum chemistry. This is something called the sign problem that crops up in other fields. All right, so why do we even want to bother to do this? We have this coarse-grained particle model. We could just do molecular dynamics simulation of the coarse-grained model. Well, the problem is, again, we still have long polymers and slow relaxation times. It's just hard to get there with particle simulations. It turns out the field theory allows increasingly efficient simulations as you go to higher density and longer polymers. You can resolve big scales. We've done simulations up to a cell that's 10 microns in a side, which you could never do with a particle simulation. And we get direct access to chemical potentials and free energies, which makes constructing phase diagrams easy. So that's the motivation. And there are two kinds of simulations once you've got a parameterized field theory. There's something called mean field theory or self-consistent field theory, SCFT. And the idea is that you don't actually have to integrate over every possible field configuration that would exist in a box. You just look for one special field configuration, W star, that minimizes this energy weight, H, okay? And the idea is that's kind of the average environment around all the molecules that they feel. So it's called a mean field approximation. And that turns out to be very accurate. If the system's dense and the polymers are long, and one way to quantify that is if the number of polymers per unit volume made dimensionless by multiplying by the cube of the coil size of the polymer, when that's a dimensionless number, when that's big compared to 1, this is an accurate approximation. And practically what it means is the polymers are overlapped, right? You're at the overlap concentration or beyond. The beauty of this approximation is the log of Z is the free energy, and so the free energy is immediately accessible and you can immediately construct phase diagrams. I'm not going to dwell on this, but we also have a strategy if you need to actually worry about those field fluctuations. We call these field theoretic simulations. And there, what we do is we run kind of a Langevin stochastic dynamics for the fields in the complex plane and sample field configurations. So that's, and this is a more recent book that talks about kind of this method in some detail. All right, and I said this is more efficient. This is a simple numerical example where we took the same model. It's the model of a polyamphalite. It's a polymer that has both plus charge and minus charge in an aqueous environment. And it was a coarse-grained model, and we simulated it in the particle representation using molecular dynamics, and we simulated it using these field theoretic simulations. This is the computational time, the CPU time on the same hardware to warm up the simulation to bring it to equilibrium. And you can see with the particle-based simulation, the computational effort grows roughly like the square of the concentration of polymers in the box, whereas with the field-based method, it's flat. And so the denser you go, you can get 2 or 3 or even more orders of magnitude computational advantage by simulating the field theory. So that's why we do it. Okay, so I am going to give you a few quick examples of executing this workflow. The first one we did, and this was Nick Shirk, it's ACS macro letters paper a few years ago. We went after this classic phase diagram. You take polyethylene oxide, very popular water-soluble polymer, is water soluble at room temperature because of hydrogen bonds between the ether oxygen and the polymer and the water solvent around it. But if you put it in a closed container and you heat it up, you will actually get a liquid-liquid phase separation. So there's both an LCST, and if you go up high enough in temperature, there's a UCST as well. So you have a closed loop phase diagram. And this has to do with breakdown of the hydrogen bond network with temperature and then ultimately entropy mixing winning again at the highest temperature. So we tried this. We took off-the-shelf force field. We did a coarse-grained mapping where each ethylene oxide repeat of the polymer was one effective bead. Each water molecule was a separate bead. And then Nick did the relative entropy, did some simulations of oligomers of PEO and water, and then did the relative entropy best fitting. Again, we used harmonic bonds and these repulsive Gaussians for the non-bonded interactions and best fit those parameters. And a crucial thing emerged that when you looked at those repulsions between the different kinds of beads, and specifically the polymer-water cross interaction, that his best fit showed that as a function of temperature, it was non-monotonic. And it turns out that's exactly what you need to get a closed-loop phase diagram. And then he used the mean field approximation to the field theory once he parameterized the coarse-grained model and drew this phase diagram. So you look at it from the distance you all are away, and it looks like, well, roughly it's the right shape. But as you start to look at it more carefully, you realize this is the experimental diagram and this is our predicted diagram. There are some issues, right? The experimental closed loop is focused on about 200 C, and ours was 100 degrees too high, right? And we're also predicting that already an oligomer of length 3 would phase separate, where experimentally you have to get to 49. So we're not getting things quantitatively right, but it's I find it kind of remarkable that with such a simple model, we can even get the rough shape right. And we can talk more in the Q&A session about why this is off and what you might do to refine it. Here's the second example. This was a project by me, Nugent, and we were collaborating with Matt Francis's group in chemistry at Berkeley. And Matt has been looking at surfactant type molecules that are built from essentially sequences that are found in intrinsically disordered proteins. In most cases, there's kind of a head sequence that's more hydrophilic, and then a tail sequence that's more hydrophobic. And when me did this project, she, as opposed to using the full letters of the amino acid alphabet, she simplified a bit and grouped together all of those that were hydrophobic into a purple bead, those that were relatively neutral, hydrophobic, hydrophilic, into a pink bead. And then green was everything that was hydrophilic, either just polar or possibly with a charge as well. So simplified the alphabet a bit to this kind of a map. And what the Francis group was really interested in was predicting the critical micelle concentration. When, as you put more surfactant in, when do you get aggregates? When do you get micelles? So we did a little, with our parameterized model, did a grand canonical calculation of where should the critical micelle concentration be. So you do a little field theory simulation in a box and converge a micelle, and then you sweep the chemical potential between that box and a reservoir that's homogeneous, and you look at where the, whoops, that's a problem. This is supposed to be the difference in grand potential between the micelle box and the other box. And when that crosses zero, that's the CMC, and you can read off the concentration of micelles. This didn't translate well. Well, if that had actually appeared, what the data you would find is that we predicted a diameter of about 17 nanometers, and the experimental diameter was like 15. And if I remember on the CMC value, the experimental number had a range between about 15 and 150. And this is not micromolar, I'm sorry, it's not millimolar, it's micromolar. So they're exquisitely dilute conditions. And we predicted 50, which is right in the middle of the range. The other thing we can do is we can actually look at the density profile through the micelle, integrate it, and get the aggregation number. And it turns out the aggregation number is about 7 in this case. So we got pretty good agreement with a remarkably simple model. The next example I'd like to talk about involves cellulose. So many of these solution formulation companies for different applications, from consumer products to paints to different things, are trying to get more sustainable ingredients into their formulations. And cellulose is a cheap, readily available substrate. As you know, cellulose is a major component of wood, and wood doesn't dissolve in water, right? And the reason it doesn't dissolve in water is because there are all these hydrogen bonds on this diglucose structure, and there are actually 3 inequivalent hydroxyl sites on those glucose rings. And the material is essentially crystalline and intractable, but you can make it water soluble if you start to do some functionalization on some of those hydroxyl sites. And a simple way to do that is to replace those hydroxyls with acetate units. And you can go to the literature and read all kinds of papers about the solubility of cellulose acetate as a function of what they call degree of substitution. So degree of substitution 1 would mean each glucose unit has one of the hydroxyls replaced by an acetate group. A degree of functionality of substitution 3 would be the maximum. All 3 sites on each glucose unit are substituted. And the problem is these things are prepared with lots of different catalysts, and nobody really knows where all the functionalization is being done on the molecule, but they do know the overall degree of substitution. And the interesting thing is, with no substitution, the material's intractable and soluble. With a fair amount of substitution, it's also intractable and soluble, but there's a kind of intermediate region where you hit the sweet spot and it works, okay? So Me decided she would tackle this beast by this method. And so what she decided was, again, we'll simplify. We'll make 8 different B types. So a completely unfunctionalized glucose unit, a fully functionalized glucose unit, and then everything in between. The 3 ways you can functionalize 1 site, the 3 ways you can functionalize 2 sites, okay? So each of those was an independent bead, and then we had water in addition. And she did a whole bunch of reference all atom simulations, obviously not using large polymers, but little fragments with varying degrees of substitution, and then did the relative entropy fitting. Turn that into a field theory model, and then tried to predict when would you have solubility and when would you not. And this is degree of substitution versus weight fraction. Weight fraction doesn't go beyond 1, so ignore all that beyond there. What she predicts is indeed at low substitution, you get a liquid-liquid phase separation, almost pure water coexisting with this dense phase. If you have too much substitution, similarly, you get phase separation, but in between, there's this sweet spot. And the calculations are not real sensitive to the length of the polymer. And just to make sure that this was all done with the mean field approximation, just to make sure that was quantitative, she took the same coarse-grained model and simulated it using molecular dynamics. So that's coarse-grained MD. And although it's hard to get free energies, you can see if phase separation occurs in a box, and then you can look at the density of the dense phase, and that's what these points are. So they're not far off from that dense boundary. Okay, the other thing you can do once you've got a model like this is you can ask questions that experimentally is not very accessible, which is, if you're going to do some substitution of cellulose, where's it most efficient to do it if you want to make it soluble? So and the answer depends on the overall degree of substitution. If you have low degree of substitution, you really want to do it at the carbon-3 site, which is this particular site. That gives you a much bigger window to miscibility, which is blue. Whereas as you go, say, more towards 1.5 overall degree of substitution, you actually want to balance your substitution between the C3 site and the C2 site, which is that one, okay, to get more solubility. So we actually have predictions for people to go and design catalysts that would be selective for just acylating those specific sites rather than generic sites. So if you want to read more about that, you can look at this recent biomacromolecules paper. Okay, I am almost out of time, but I want to just kind of quickly walk you through one final example. The examples I showed you previously were all in water. This is an example in oil. This was a project with Mitsubishi where they were interested in some acrylic block copolymers that you add to oil, and these are used as viscosity modifiers, and they keep the viscosity flat with temperature because of changing self-assembly characteristics. And the expectation is that these things would form micelles or mesophases at high enough concentration in the base oil. So as a base model oil, we took dodecane. We modeled it using 4 carbon beads. So a dodecane has 3 beads on the molecule. And we were specifically looking at polybutyl acrylate, which has effectively 1 bead on the side chain, and polydodecyl acrylate, which has a longer hydrocarbon tails off each monomer. And those were 3 beads each. So that was the model. Charles Lee, who led this project, then did simulations of the oligomers, parameterized the coarse-grained model, and tried to predict a phase diagram in the coordinates of the mole fraction of butyl acrylate in the dye block versus the fraction of polymer that's put in the oil, okay? And he predicted, this was all at 20 degrees, and he predicted that the phase diagram would be homogeneous in here. There's a 2-phase region where you have polymers that are rich in butyl acrylate. Butyl acrylate doesn't like the oil as much as the dodecyl acrylate. But over here, there's a region where you can have all these ordered mesophases. So Charles then went to my colleague at Santa Barbara, Craig Hawker, who's a superb synthetic polymer chemist, and worked with a couple of students in the group, Elizabeth Murphy and Stephen Scala. They made some beautiful model materials, very low dispersity, overall degree of polymerization about 150. In this particular sample, mole fraction of butyl acrylate was about 0.4. Then mixed these in dodecane oil at different concentrations, did Sachs measurements, and were able to index a bunch of peaks and identify, indeed, this was a hexagonal mesophase or a BCC mesophase, et cetera. In the meantime, Charles was filling in that mesophase region, and they overlaid the two. So this is Charles's phase diagram. The shaded area, this is where hex should be stable, BCC, face-centered cubic packing of spherical mice cells, and then this is disordered. Those data points are from the scattering experiments, and you see really nice overlap. This was a second sample. This one had 53% butyl acrylate, a little smaller in overall molecular weight. Theoretically predicted diagram, and again, now the hex region is much bigger, and that's consistent with experiments. And then finally, the third sample, 74% butyl acrylate. You see now the lamellar layered mesophase has taken over a much bigger part of the phase diagram. And now we're missing those boundaries. Experimentally, they're kind of shifted to the right relative to the theory. We expect that's because when we parameterized the model, we did it at 50-50, and this is the sample that's kind of farthest away from 50-50. But again, you know, the ability to first principles predict phase diagrams like this with such a simple model is we think is pretty neat. Okay, so I will stop. Hopefully gave you a little idea for what we're doing in this space. I'll leave up these references if you're interested. We have kind of a de novo formulation design tool where we can predict things with literally no experimental data. So with that, thank you. Be happy to take a few questions.
Distribute the microphone as needed. Questions?
Thanks so much, Dr. Fredrickson. I love Scott's work on relative entropy. And one of the questions I have about it is with the matching the relative entropy or minimizing the relative entropy with fragments, what are we missing in the entropy of the polymers where the entropy as a function of degree of separation is what makes them so interesting? Is there a measure of how much we might need to squish a phase diagram or shift a phase diagram that gives us some information about that?
Yeah, so it's a great question. The beauty of this approach is I mean, what you're missing are some end effects. Basically, we need the oligomers kind of long enough that the end contributions are small compared to the middle bit, right? But what we do is, you know, all those atomistic simulations are done with little fragments of the polymer. When we go to the field theory, we scale up to the full polymer. And the field theory, because it's a physics-based field theory, it knows about polymer entropy and how it scales with size. So all that is preserved. But you could ask questions about, you know, in best fitting all these parameters, we're missing end effects. And so, yeah, I mean, you could try to put a different bead at the end and fit that explicitly, okay, which would be an approach.
Short follow-up to that. I'm curious in looking at the workflow here, and I'm somewhat familiar with what's required in these simulations and so forth, that how about the relative entropy step? Is that a demanding part of the workflow?
Yeah, if you didn't have Scott's software for doing all this, because, you know, you have to, I mean, it's a data science kind of problem. You've got all these configurations from these reference all atom simulations. You've got tons of data, and then you need to filter them and map them to the coarse coordinates, right? And then you have to process that data. I mean, essentially, the optimization step involves computing averages using both those all atom reference configurations as well as some data you get from simulating the model at the coarse model at the current lambda values, and then you have to adjust the lambda values in a descent method, right? So Scott's group over the last couple of decades have developed all that infrastructure. So we brought the field theory side, they brought that machinery, and we just kind of put the two together.
Yeah, it strikes me as a multi-dimensional kind of minimization scheme that could be.
Yeah, but I mean, you know, our students are, you know, getting the reference data and doing the fitting, so they they have a throughput of a few models a week maybe, but we don't have a lot of computational resources. If you threw a lot more, you could get higher throughput than that.
Thanks for the nice talk.
Yeah, sure.
It's not my area by any means, so it's a really probably dumb questions, but on the relative entropy aspect, you showed this really smooth parabola that would be trivial to minimize, right?
Yeah.
What's it really? Is it really that smooth?
No, it's not that smooth. It turns out you can prove that if you have a model where all the parameters appear linearly in the potential, there is one absolute minimum, and it's essentially that surface is convex, and you will get it. But the problem is most of these models, we have parameters appearing nonlinearly, like the range and the potentials. And then you got to worry a little bit about how you did that optimization, and do you get stuck somewhere in a suboptimal basin? And that just requires a little bit of exploration, starting the optimization from different initial conditions and making sure that the answer you're getting is robust.
And are you able to do that before you get to the experimental comparisons?
Yeah, I mean, we do that as part of the computational workflow. You know, they don't start a relative entropy simulation optimization from just one initial condition. Yeah. So there's still art in all this, right? I mean, there are a lot of decisions you can make along the way, and both the mapping procedure, the training procedure. So we're kind of trying to figure out what's best practices and what works and what doesn't.
I was going to ask another question, but I realized we have an hour later, so I'm going to save some. Who else has questions? Maybe my lab?
So near the beginning of your talk, when you first got into the application, you were talking about the diethyl ether dissolving in water. And you were saying that it's possible you could go a little bit more in depth in why there was some errors there.
Yeah.
And what you could do to improve them.
Okay, thank you for reminding me about that. And a final obligation of the talk. So, I mean, the biggest, misalignment is we're 100 degrees predicting this closed loop is 100 degrees too high. It turns out the answer is exquisitively sensitive to the force field, that classical force field that you start with. And we found by just and these force fields have partial charges, say on the oxygen, a partial negative charge, right? And then more of a partial positive charge on the carbon atoms. If you fiddle with those partial charges just 5% in a different direction, you get a 100-degree shift in the prediction of that closed loop. So I think in many cases where we don't get agreement, it's not the problem with our workflow, it's the problem that the starting force field is just not accurate enough, right? And so, we can't do much about that. The beauty of this workflow is it'll be the same, and when there are better force fields at the front end, you can make better predictions, and you don't have to change the way you're operating. But then the second issue was that we're predicting that very small ethylene glycol oligomers will phase separate when experimentally you have to go to up to about a 50 mer to get that. That is, I think, more associated with the mean field approximation, that if we relax that we'll probably get better answers on the size effect. Because for those systems, when the phase separation is going to appear, those boundaries are very sensitive to thermal fluctuations, and that's neglected in the mean field approximation.
So just a quick follow-up. You said vary by 5% on the partial positive and partial negative charges.
Yeah.
How much does, like, let's say you were looking at the charm versus the amber force field, how much does it do those force fields vary?
As much as that, if not more.
Okay.
Again, there seems to be an art to the selection of force fields, right? Some are better for some class of systems and worse for others. And the people who do this for a living, I'm not an atomistic simulation person. I rely on Scott's expertise there. But the specialists kind of know which ones are better. But in reality, you don't really know until you compare with some real data.
I'd just like to ask a clarifying question. For your field representations,
Yep.
do you still have the coarse-grained beads in there, and then the potentials between them are just?
Yeah, so I mean, essentially as I described, you take a many polymer problem and you reduce it to a one polymer problem in a field. So you just need to do the one-dimensional statistical mechanics of a polymer, and we numerically do that by a kind of transfer matrix calculation. So the inner loop of our simulation is we're recomputing that partition function of a polymer feeling the field. And every time you update the field, you have to redo that calculation. But there are no beads that we're sampling or moving around. It's a kind of transfer matrix calculation.
Thank you.
I have some other bad questions.
Well, I liked your last one.
Well, one thing is you talked about applying a potential. I think
Yeah.
when you were setting up the mean field model, there's that, or
Well, we
before
actually
the mean
we
field.
apply the potential to the all atom simulation to force a composition in homogeneity, so that within the box there's not only almost pure A and almost pure B, but there's everything in between.
And what
right?
is that field?
Literally it's a field that will selectively push on one component in the mixture versus the other. So I mean, literally, it's a sinusoidal potential.
Is it a physical?
No, it's
Analog,
just there to force mix separate phase separation to varying degrees. And then when you best fit the coarse grain model, you have the same potential present, and you're trying to match again the distribution. But because you're doing it in a way where you've forced composition variation, the model kind of says, well, I can't just do well when it's all an A environment or an all B environment. I have to do well at intermediate compositions. And you end up with a model that then, when the system on larger scales phase separates, does a better job.
Yeah, I was going to ask if that's important for the phase separation component.
Yeah, because like those examples that I showed you, we had phase diagrams in this last one, the oil example, as a function of volume fraction of polymer in the solution. We would have had to reparameterize at all those different compositions if we hadn't done this trick. So we just do it at one composition, but we have to reparameterize at every different temperature.
A follow-up would be, you talked about integrating in a complex plane, and that makes me think of how do you handle singularities in that situation, and then are the phase separations singularities in this?
No, it turns out that the field theories are actually that Hamiltonian function is actually an analytic function of the field variables. So there actually aren't nasty singularities out in the complex plane. Turns out people who try the same trick that we use for simulations in quantum systems where the degrees of freedom are fermions, those models have horrible singularities and the method doesn't work. So the method only works for quantum systems with both statistics or classical systems where you've got no nasty singularities around. Yeah.
Thanks.
There's one in the back.
Peter.
Thank you. I believe I'm even further away from your field than my colleague Elton Gronyard, so please forgive. You motivated your talk with the experimentalist problem of figuring out in this entire space, where could I go? How can I make a better material or better solution? And you showed that with this workflow that you have, you actually can predict some properties, at least qualitatively well,
Yeah.
and actually it's surprisingly well in some cases. The question I have is now in your task, and I don't know if this is, I suppose that this is the task since you started with the motivation this way, but getting actually to helping the experimentalist, you might want to be a little more closer to what actually is there in an unknown system. And when you look at this, all that you have here, how close or how far are your, what are the missing things that you might need to add to your process to actually get really to help the experimentalist?
Yeah, well, it's a great question. Yeah, I mean, the overall motivation was to be able to use these tools to scout promising regions in design space that experimentalists could focus on, right? Because the search space is just enormous. Often there's motivation for changing a formulation that, you know, if you're Procter and Gamble and the consumer is telling you, we want to read on the label that, you know, there's all kinds of biodegradable, sustainable components, and that they think they can sell more product for a higher price because of that, they'll want to swap out some of those components. The problem is the current recipes are highly optimized by trial and error, mixing things and the way different components interact. So they have kind of no, you know, you take one component out, you put a sustainable substitute in, you break the property set, and they have no idea which way to go. So the hope is, you know, with a lot of computing power, you could just be grinding away on trying to make some predictions about what directions to go, and that would both accelerate and lower the cost of the experimental optimization. So that's kind of how we see it going. Ultimately, it'd be nice to go the inverse design where you specify the property set you want and go backwards to the chemistry, but that's a harder problem.
All right, I think in the interest of time, we should probably wrap up here. Please join me. Let's thank Glenn one more time.
Sure.